Mike coming back at you here with another video on Calculus 1. In the previous video, we saw several sample problems as to how do we use the chain rule to come up with the derivative for a composition of two functions. And if you think back to last video, we ended that video with a sort of odd looking sample problem where we had a composition, but one of the functions making up our composition was just sort of an arbitrary random function g of x. And we said that that particular sample is going to nicely lead us into our next video. That is to say, this video right here. So today we are going to talk about implicit differentiation. For the most part, in Calculus 1, when we're looking at curves or functions, we can typically write these things as y is equal to something just in terms of x's, like y is equal to x squared, or y is equal to the sine of x. And then finding the derivative, dy over dx, is really nothing crazy. It's nothing that hard. But not all curves and not all graphs can nicely be written as y is equal to something. Just for some basic samples, circles have equation x squared plus y squared equals some number. An ellipse has equation x squared over a squared plus y squared over b squared is equal to some other constant. So we can't write all nice curves and all nice graphs of shapes nicely as y is equal to just something in terms of x. But we still may want to know information about the derivatives of these curves. That is to say, we want to know slopes of tangent lines. So we need to come up with some other way to find dy over dx for these curves. And this is where the technique of implicit differentiation comes in. So we have a sample problem here. We see that this equation contains both x's and y's, and we also see that it contains varying powers of y's. We see we have a y squared on the left-hand side, we have a y on the right-hand side, and then we have varying powers of x on the left and right-hand sides as well. Now, some equations that would look odd like this, it could be possible to move things onto one side and just do some basic algebra with it to get y by itself on one side and then everything with x's or constants on the other. But in this particular case, we cannot do this. So when we look at an equation like this, where we have x's and y's, and possibly varying powers of y's, or y's being plugged into other functions, we're going to see some of these examples in the next video. We look at this equation and we work with these equations, understanding that the y's are secretly functions of x. Secretly, or the technical term, which is going to be implicitly. The y's are implicitly functions of x. And our end goal is that we want to find what dy over dx is going to be. Now, sometimes this visual of just seeing y's, but having to think of the y's as some other function of x, that can get a little bit confusing. So there is another way you can rewrite this if you so choose. You can simply replace the y's with functions, and I call them g of x here. So we see that the y got turned into a g of x there, and then this y got turned into a g of x there. So this is just something you can do just to help keep your mind straight as far as what we're working with. We now have these things just in terms of x, so perhaps visually this is a bit more friendly. But now the question is, how do we actually come up with what dy over dx, or what g prime of x will be, based on whichever way you want to look at it? It comes down mainly to a three-step process. And by far, the first step is the biggest hurdle that you have to overcome. Once you get past the first step, once you get through that first part of it with no problems, the rest of it is just moving terms onto one side or the other, pulling out a common factor, and then dividing on both sides. But that first step is the key piece to this entire process, which is the process of implicit differentiation. So we're going to work with this same sample here, and we're going to go through this guy step by step. We're going to find dy over dx for this equation, or shall we say for the curve that is implicitly defined by this equation, by using the technique of implicit differentiation. So you're given your equation. Step one, you're going to differentiate both sides of your equation with respect to x, keeping in mind that the y's are secretly functions of x. So starting with the left-hand side, we have 4x cubed. Take the derivative of this thing with respect to x. This is just a basic power law, nothing crazy happening here. Where it starts to get a little bit confusing is when you are differentiating y terms. So as we saw in the previous slide, we could look at this term here as 2 times g of x squared. So I see 2 times some arbitrary random function of x squared. I'm going to be using the chain rule here. Chain rule says if I differentiate a function of x raised to some power, then that power comes down in front, times that function on the inside raised to a power 1 less than the one we had, times the derivative of that inside function. So that 2 that's in the exponent is going to come down. This is what we get as a result of taking the derivative of the 2y squared here. So this 2 is going to come down and multiply with that 2 to give me 4. Times that g of x raised to a power 1 less than the one we had. So we have g to the x, or g of x raised to the power 1, or just g of x, times g prime of x equals, now we have 5 times g of x here. And we know that when we just differentiate some random arbitrary function g of x, we just get left with g prime of x. So all this stuff corresponds to that term there, and then this term here is our 5 times g prime of x. And then plus the derivative of 6x, again, nice and basic, it's just 6, and then the derivative of a constant is 0. Now, I wrote 4y times dy over dx on the left-hand side, and then 5 times dy over dx on the right-hand side. This is just all based on which way you want to look at these y's. If you want to leave them in terms of y, you would have y's in dy over dx's. If you wanted to change the y's to g of x's, you would have g of x and g prime of x showing up in there. I'm really saying the same two things right here in this second line. So this is the hard part. This is the biggest hurdle that people tend to get tripped up on when you're doing implicit differentiation. Once you get past this part with no trouble, then from here it is smooth sailing. And what we're going to see at the end of this video is we're going to see a little bit of a shortcut that you can use just to help you get through these problems and to help you at least come up with the right answer. So now we're on to step 2. Now that you have differentiated both sides of your given equation with respect to x, you're then going to move all the terms that contain a dy over dx onto one side, and all the terms that don't have a dy over dx in them onto the other side. So you can see I took this guy and moved it over to this side of the equation, and then I took that 12x squared and moved it over to the right side of my equation, and that gets me my second line there. Last step, you're going to pull out the common factor of dy over dx on whichever side you have those terms. It does not matter which side you move things to, still going to get you to the same answer in the end. Once you pull out that common factor, you are going to then divide both sides to get dy over dx all by itself. So this is where we left off from step 2, our first line here. You can see that I pulled the dy over dx out of both of those terms, leaving me dy over dx times the quantity 4y minus 5 equals 6 minus 12x squared. And then lastly, divide both sides by that 4y minus 5 just to get the dy over dx all by itself. And that is how we solve for dy over dx. So 3-step process. Differentiate both sides with respect to x. That being step 1 is the biggest hurdle. Step 2, move all the terms with a dy over dx onto one side of your equation, all the terms without dy over dx onto the other side. Step 3, pull out the common factor of dy over dx, and then you are going to divide. Now here's why I said that what we did in the previous video was going to be so critical to what we are doing in this video. Most of these problems, when you have to find dy over dx using implicit differentiation, you'll be having y's raised to some power, or maybe x's times y's. But anytime you differentiate a y, you're really using the chain rule. Chain rule is such a critical rule to know in any Calculus 1 course, and you have to know that guy stone cold, because this is just one case where we use the chain rule. And we're going to see it being used very, very, very often in this section, in this topic. Now, here's the shortcut that I promised we would get to. It's pretty common for people to have lots of trouble in step 1 of this 3-step process, and they just can't quite seem to come up with what they should come up with at the end of step 1. Having to differentiate those y's just seems to give people some problems. So here's the shortcut that I offer. Here's what you can do just to get past that sort of visual confusion and at least get you through the step 1 without any trouble. When you come to a y and you have to differentiate a y, pretend that it's nothing special, and you're just going to take the derivative of it like it's any regular variable, like x. However, and this is the key thing that you have to be sure to do, when you differentiate a y, after you have took the derivative of it like it's been nothing special, just multiply by dy over dx at the end of that term. So I'm going to go back to the problem that we did, and we're going to look back at it in that light. We're going to sort of draw out here what we mean by this guy here. So first problem here, no troubles whatsoever. I now come to that 2y squared. So how you would use this shortcut is you would look at your 2y squared and go, okay, I'm going to think that this is actually 2x squared. I'm going to pretend that there's no y, that it's just some x. And we know basic power law. We know how to come up with the derivative of 2x squared. We know that it's a basic 4x. So we're going to pretend that this is just 2y squared. When we differentiate it, it gets us 4y. So that's why we come up with the 4y there. And now here's that key thing. Here's that key piece. Because we differentiated a y, at the end of that term, we have to multiply by a dy over dx. Anytime you're differentiating a y term, there should always be a dy over dx at the end of that resulting term that you get. If you differentiate a y term and there is no resulting dy over dx at the end of that term, then you have gone wrong, and your final answer is not going to be quite right. So this is the three-step process for finding the derivative of an implicitly defined curve. This is how we find dy over dx using implicit differentiation. In the next video, we are going to take a look at a couple sample problems, and we're going to go through these guys step by step so we can get more practice with using the technique of implicit differentiation. If you have any questions or comments, be sure to leave them in the comment section below. Otherwise, until next time, guys, take it easy.